Ladies and gentlemen, it's time to set sail. And we're headed to a truly special place today, Safety Island. Sounds like a pretty serious place, huh? Or maybe a reality TV show? The safety island we're talking about today is a very important element if you're looking to meet functional safety standards like ISO 26262. Safety islands ensure reliability for time critical functions in automotive applications. And if we're going to discuss safety islands, we should probably talk about companion microcontrollers too. Hi, I'm Amelia Dalton, host of Chalk Talk. Companion microcontrollers are a vital element of today's complex automotive designs. In this episode of Chalk Talk, Matt Goodavish from Infineon and I investigate how the architectural evolution in automotive design has impacted the need for companion microcontrollers, the role that safety islands play in the development of these systems, and the core system benefits that companion MCUs bring to these kinds of designs. And before we get started, don't forget to click that link. There you can find even more information about this topic from Infineon. Hi, Matt. Thank you so much for joining me.
Sure, no problem.
Okay, so we're talking about how we can improve the cockpit computer with the help of companion microcontrollers today. But first, Matt, can you tell me what exactly is a companion processor?
To be honest, there's a lot of different definitions out there. So I'm glad you asked that question. From our view, we consider companion microcontrollers to be a microcontroller that's assisting what we call SoC or system on chip. It's doing different functions that the SoC either isn't capable of doing or isn't suited to do. And we'll talk about that a little bit later. However, there's also the question of what name specifically do we call a companion microcontroller? And there's different definitions out there. We've heard VIP, vehicle interconnect processor, DCU, digital control unit, and some others. And that's just around the companion micro. Then you have the SoC, system on chip. There's other names for that too, application processor, central processing unit. But it doesn't really matter. What we really mean by a companion microcontroller is just a small little computing center that assists a main processor.
Fantastic. Now, Matt, how has the architectural evolution impacted the need for a companion microcontroller?
Yeah, so originally, many, many years ago, we had individual domain type systems that were focusing on one particular domain, like infotainment or ADAS or others. And those were typically run by microcontrollers or powerful microcontrollers, and SoC really wasn't in the picture. But then, as you start getting more horsepower and processing needs in these systems, even the domain systems started needing these SoCs. And that's really when you started needing a companion micro. Today, we're even transitioning to what they call zonal type systems, where there's a central processing center, either one, two, or three. They often call those high performance computing centers. And each of those would have one or more SoCs as well, which again would need a companion microcontroller. And as we move forward in the future into what we call a car computer, those needs are just going to continue to increase. I'll show you a little later some really interesting things that are trying to be put into these SoCs. And we need the SoC to focus on what it's good at and use the microcontroller to focus on more companion micro functionality needs.
That makes sense. Now, Matt, walk me through the different processes included in these different computational setups.
So typically, you'll have a application processor, companion microcontroller, and some other supporting memories and security functions and components. What's important to note is this application processor often isn't a automotive grade device. They often take these consumer devices and certify them for automotive use. Furthermore, they're running completely different operating systems than a lot of the automotive car manufacturers need in some of these lower level functions. So typically you're looking at a Linux based OS, Android, something like that. And by doing that, those OSs, they focus on different things and different priorities. They're more UX or user experience focused to make sure that that end application is running correctly and smoothly. Furthermore, these application processors are connecting to a whole host of different things like displays, a whole host of sensors, and other processors, even that are contributing to the overall application. Finally, as AI functionality becomes more of an important need, I think you can imagine just how heavy a load these application processors are going to take on. So then on the other side, you have what we're calling the companion microcontroller that we mentioned. And because of the heavy load of these application processors, these companion micros are even more so needed. So these are automotive specific MCUs, and they're running a real time operating system or RTOS, such as AutoSAR or one of the other ones out there. And the purpose of that is so that you have expected behavior at set times and tasks running in very specific time frames. So it's very orderly and it really is conducive to safety within the vehicle. Furthermore, there's other things that the application processor just can't or doesn't need to focus on, like communication interfaces, different analog functions, and those kind of things. And I think across the entire system, and you've probably heard this before, functional safety is very, very important in a lot of applications. And when you start talking functional safety, especially in the automotive world here, there's very specific standards that you have to adhere to on the system level. And these companion microcontrollers help you get there.
All right, so let's talk about safety. Now, there is a need to separate safety applications in these kinds of designs, right? Matt, talk to me about how that is divided up between the companion MCU and the application processors.
Absolutely. So, like I said, this is a very, very important thing within the automotive space. And there's something called ISO 26262 standard. And this is an automotive standard that pretty much everyone adheres to in the automotive world. The important thing is these application processors, they weren't really developed per that standard. And to really bring a device up to these levels, you do need to, from design up, build and conform to the processes that these standards kind of put out. So then what do you do? Do you stop there? Well, absolutely not. You still can get a functionally safe system, right? You just need to add additional things like the companion microcontroller. So these application processors, they're going to do their job. They're going to focus on being quick, getting that user experience out to the end user smoothly, and they're going to make sure that all those application functions I showed earlier are running very fast. The one thing I would say is these operating systems, I want to touch on that again, they're not real time. In the ISO 26262 area, you need to have very specific things happening at very specific times. So on the companion microcontroller side, it lives up to that. And it depends on which application you're talking about. Some applications require ASIL B level, others up to ASIL C or even ASIL D level. The different companion microcontrollers that a supplier will put out will conform to each of those standards in different ways. In the end, it's all doing things in this real time fashion. The other thing is these companion microcontrollers, they can monitor this application processor and let you know when things are going wrong. They have built in safety mechanisms often that are in the hardware that are going to protect the whole system. And let's say something does go wrong, it can then record that failure so that you can go back to it later on and figure that out and fix it in the future. So overall, we here at Infineon, we've got this ProSil standard that lets you know that something is ISO compliant. And we give an example down here of a cockpit application or infotainment application where on an instrument panel, you might have to have some areas monitored. And if something goes wrong in one of those areas, you might want to put up a little symbol to let you know it's going wrong or an overlay. And that's what we're meaning that these companion microcontrollers can help you do things like that.
Very cool. Now, Matt, there has been a term that I've heard lately called safety island, which relates to these kinds of designs. Can you talk a bit about that as well?
Yeah, so this is more in the SOC space. So SOC suppliers focus on this of should we add a safety island, should we not add a safety island? And what that is essentially it's a walled off area on an SoC die that's going to do all these things that a companion microprocessor would typically do externally, but on that SoC die specifically. So typically, you're going to have in the normal part of the die different things like application cores, signal processing units. You've got your dynamic memory, a bunch of different communication peripherals. But then you'll have this walled off area where you have to have pretty much all the resources of a microcontroller, and you have to have a separate operating system, real time operating system running on that specific walled off portion so that it can do all these functionally safe things that are required in its own little space. And that might sound great, right? But obviously, this increases cost, this increases complexity and time to develop things. And even some SoCs out there that may have a limited safety island, often they're going to be recommending still a separate companion microcontroller to assist, even in those cases. That's really what we mean by the safety island is walled off area of the SoC to do companion microcontroller functions.
So, Matt, I imagine there are a lot of different ways to put together the companion microcontroller with SoCs. So, can you give us an example?
Absolutely. I'm showing right here a cockpit or infotainment example. And there's a whole lot of different applications and ways you can put these things together, but this is something we typically see in that application. And the first one in A1 there, you're going to have a couple devices, two SoCs, each running a separate operating system doing specific things for like two different displays. And then you're going to have the Treveo microcontrollers assisting those MCUs, again, running a separate operating system. So there's a lot of different pieces there. It's very modular, but the price level isn't typically too great. And we don't see that kind of a system often today. A2, however, we do see quite often where you have a single SoC running a couple different displays or functions. And you got this thing called a hypervisor that's coordinating different operating systems and routing tasks to different operating systems. So it's kind of all in one doing one thing. Then you also have the companion microcontroller next to it, again, running a separate real time operating system. So this is very popular. And kind of the same similar set, you got A3 there, where the SoC does try to implement a limited safety island. But again, they're recommending still to have that companion microcontroller to do other communication functions and analog functions that the SoC just can't do. And we'll dive into those later. But then A4 is really getting interesting because it's probably the most cost efficient level on a BOM basis where you can actually use a companion microcontroller in place of some SoC functions. And this one here is showing where there's a graphics microcontroller running a complete cluster system. It's got its real time operating system. It has some other, these typical SoC tasks running on it. You still have another SoC for the IVI system over on the IVI display, but this really does cut down some components and cost. So that's going to be one big thing that we're asking people today to think about is if you're going to use a companion microcontroller, which is often needed, what else can you do with it? And we want to help our customers find interesting new ways and things to do with it.
Fantastic. Now, Matt, when it comes to core system management, what do you think are the biggest benefits that a companion microcontroller can provide?
Yeah, well, this is really at the root of why these companion microcontrollers are often recommended. So, in one case, you have power supply. So, if you have a companion microcontroller, it's got very simple power supply requirements, so it's not hard to implement. But also, like I said earlier, you can monitor the SoC itself on boot up during runtime, and it even can shut the SoC down in certain cases if there's some kind of disruption in that power system. And one thing I would say is SoCs take a long time to boot up those different power rails that they have on them, right? And the microcontroller is a lot quicker. So while those SoCs are doing their thing on the power rail side, the microcontroller can already be 5 tasks in or 10 tasks in doing something else. Then you also have thermal system or thermal management to think about. So think about being out in the hot Arizona sun and the heat burning down on the car. And all of a sudden, the SoC is getting really hot. And it's typically rated a lot less than these companion microcontrollers may be rated at. Because again, it doesn't come from these automotive standard sets. They're brought up to that afterwards. So if it's getting really hot, there could be an issue. And this companion microcontroller can detect it early, shut down the SoC, and then give warnings to the users that something's going on. Of course, it's going to record that for later, diagnosis, but it's really about that real-time engagement to get that SoC controlled. Then on the boot side, kind of mentioned this a little bit earlier, the MCU can boot up very, very fast. Think about you looking at a central information display in the center of a vehicle as your car boots up. The MCU might be able to put out maybe a splash screen or some interesting graphics or even interactive graphics from just a couple milliseconds after booting up. And then the SoCs behind the scenes is taking its time getting all those different OSs we've talked about, all those different functions and tasks up and running. And eventually it's going to transfer the SoC, but the MCU will allow you to do it a lot quicker. And finally, from a redundancy standpoint, the companion microcontroller can do what's called plausibility checks or even challenge response checks. So essentially, these are things that are just looking at what's actually happening in the system, making sure different inputs are correct. And then if they're not correct, they can take action right there in the companion microcontroller while the SoC can still focus on what it does best, and that's the application.
Okay, so are there any other benefits beyond core system management?
There definitely are. One big one's security. A lot of time people think of just the actual car operating, but what about after that car gets disposed of and these modules go to either a second use case or they're themselves disposed of? Often you want to lock the system down so that bad actors can't get in there and do things or get at data or whatever it is, right? So these companion microcontrollers can actually go through a lifecycle management system where, and the diagram here we're showing, it only goes one direction. So once it gets programmed, once it gets up and running into that secure state there, then once the overall module is disposed of, it really can only be diagnosed and you can't really operate it anymore. So that's there to protect the data and what's going on within that system after the thing's disposed. Furthermore, we got other communication and vehicle interface functions. SoCs typically don't have certain peripherals where the companion microcontroller might, especially on the analog side. So you can actually do things. This goes back to things that the SoC just can't do on its own, right? It needs some external component to do that, typically an analog component. And the companion microcontroller is perfectly suited for that. But then you get into these really neat things that we're talking about, and we show one example here in an extra benefit, what we call video safety companion. Again, this is an infotainment use case, where if you're already needing this companion microcontroller, where in normal cases here, we're showing an SoC passing graphics through it to a display, and really all the companion's doing there is the typical base functions we mentioned earlier, plus it's monitoring those graphics, and if there's a problem, it will put up some kind of warning on the display. Now, what's really neat about this is if the SoC fails completely, the video stream fails completely, then the companion microcontroller can actually put on a full instrument cluster still on the display. So a lot of cars will just put like a small little light or indicator saying something's going wrong and your display goes black. I don't think anybody wants that. In this case, you can do an even better scenario where you actually have a full instrument cluster. So this is just one of the interesting new things that could be done. And there's a whole host of other ones that we're more than happy to talk with people about if you reach out on this topic.
Fantastic. All right. So, Matt, what specific benefits do Infineon MCUs bring to these kinds of systems?
So we have a very wide range of potential companion microcontrollers. And I say potential because it really depends on the use case of the application. So typically for an A so B level system, you're looking maybe at a Treveo body or a Treveo cluster that we mentioned earlier there. And these microcontrollers have all those different analog functions that we mentioned earlier, the different communication interfaces, and they can get you up to that A so B level very quick. Then you also have what we call the Oryx family. These are more powerful microcontrollers to do everything that those base companion microcontrollers might be able to do. Plus, it adds more horsepower and oomph to the system where if you want to do some of those interesting use cases, right, that I was talking about, or maybe offload some things from the SoC, the Oryxes might be a potential there. These Oryxes can do even up to ASIL D level functional safety. So really we got everything you need from a companion microcontroller to fit whatever bill it is in your particular application.
All right. So, Matt, to recap, why should my audience choose a companion microcontroller for their next design?
Yeah, so I think over the course of what we just talked about, we talked about a little of, what the SoC does, this application processor, and maybe some of the benefits of using it, maybe some of the downsides of things that you got to watch out for. And we also looked at this safety island, and I'll say right now, it can be done, right? You can put all these companion functions into the SoC. But again, that's going to be very expensive, very power hungry, and it's going to really extend the time for development. A lot of SoCs today are still recommending a companion microcontroller. Again, for all those different functions that we mentioned, whether it be the functional safety, the real-time control where you have predictable behavior and you can record your failure conditions, the different communication interfaces, powering up the SoC, shutting down the SoC if there's problems, and all those interesting specialized functions that we talked about. It's really that last piece I want people to latch on to because I think in today's world of automotive, there's not really a question of should you need a companion microcontroller or not. I think we've proved that you usually do. But if you're going to use it, what else can you do with it? And that's where we really get excited. So, in short, we recommend always to use that companion microcontroller with an application processor. It's going to save you development time and effort. It's going to be more flexible, and we're here to help.
Fantastic. Well, Matt, I think that's all I have time for today. Thank you so much for joining me.
Thank you, Amelia.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from Infineon. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EEJournal.